So some things that we've been talking about in this unit is the idea of enthalpy change, and that's the change basically in what I like to call the chemical potential energy of a substance. And there's more to that definition, but for us, that's enough right now. We know that enthalpy is the change in the system, the change in our chemicals. That means we can't measure it directly. We have to find it through the change in the surroundings, the change in heat of the surroundings. Of course, heat is thermal energy, and thermal energy is transferred between substances due to a difference in temperature. And we know that heat always moves from something that is warmer into something that is colder. And you'll notice enthalpy is denoted by a capital letter H, and heat is a lowercase q. Yes, a q. Um, H was taken by enthalpy. E is the Euler constant. A has a meaning in kinetics. T, lowercase t, is time. So all of the letters in heat were taken. So I guess we get Q. So let's think about how we can use these quantities. Okay. Enthalpy change is an extensive amount. An extensive property means that it changes as the amount of matter changes. And so if you think back to what we saw in our EndoExo lab, the more magnesium we used, the larger the strip, the more heat was produced. And we saw a larger change in temperature in the surroundings as we went from a small strip to a medium strip to a large strip in our exothermic reaction. So the amount of heat produced or the amount of change is extensive. That means that we'll have to look at the enthalpy change for 1 mole and multiply that by the number of moles involved. So in AP chemistry, you'll see this unit a lot. The unit for delta H is kilojoules per mole of reaction. And that actually helps you really, if you use your units, to guide through a problem. So let's look at a problem that uses delta H. Okay. When 1 mole of methane is burned at constant pressure, 890 kilojoules of energy is released as heat. So energy is being released. That means this is exothermic, and delta H should be negative. So really, we could actually say that this is minus 890 kilojoules. That's kind of put in there in the released as heat. So it says to calculate delta H for a process in which a 5.8 gram sample of methane is burned. And we need to balance the equation first. Okay, so if we balance this equation, we see 1 carbon, but 4 hydrogens, which means I can make 2 H2Os. And that means I'll need 2 into 4 oxygens. So I'll need 4 oxygens to get 2 H2Os. So now my reaction is balanced here. So I'm looking at 5.8 grams of methane, and 1 mole of methane is 1 mole of reaction. And so a mole of reaction is exactly how it's written on the page 1 time through. So 1 mole of methane is used up in 1 mole of reaction. But 2 moles of oxygen gas are used up in 1 mole of reaction. And 2 moles of water are produced for 1 mole of reaction. So this essentially acts like a conversion factor. Well, 5.8 grams is not super helpful because this is kilojoules per mole of reaction. So let's take that 5.8 grams and convert it into moles. That means we're going to divide by the molar mass so that the grams cancel and we have moles. And that gives us 0.36 moles of methane. So now we can use that to find our amount of heat because our unit for delta H is kilojoules per mole. So let's set this up. Delta H in kilojoules per mole. Okay, so that's moles of methane. And looking at the equation, we see that 1 mole of methane is 1 mole of reaction. And then we can use the information from the problem. For 1 mole of reaction, we have 890 kilojoules of heat. And since that heat is released, it's exothermic, and my delta H must be negative. So I take this and do 0.36 times 1 divided by 1. That's 1, 0.36. And then I multiply that by the negative 890 kilojoules. So if we take a look at that, we end up with the answer being minus 320 kilojoules. Two significant digits, then we had 5.8 grams. So using the mole of reaction is really helpful for us. It gets us from talking about moles of methane to moles of the whole reaction, which allows us to work with kilojoules over the whole reaction. Okay, so let's try another one. Okay. So here's my reaction. This is actually the reaction from part 1. We have sodium hydrogen carbonate reacting with an excess of citric acid. And we find that the delta H here is positive 210 kilojoules per mole, which makes sense because in our lab, we figured out that this was an endothermic reaction. Products were higher energy than reactants, so delta H is positive. And so we want to find out what happens when 345 grams of sodium hydrogen carbonate react. Well, you notice delta H is in kilojoules per mole reaction again. So we need to get the moles of sodium hydrogen carbonate. Okay, well, moles of sodium hydrogen carbonate means we need the molar mass. That means I'd add up a sodium, a hydrogen, a carbon, and 3 oxygens to get about 84 grams per mole. So we can find out how many moles are reacting then. 345 grams, 1 mole over 84 grams. Grams cancel grams, of course. We get 4.11 moles of sodium hydrogen carbonate. So now I can use this to work with my number in kilojoules per mole reaction. So let's set this up. 4.11 moles of sodium hydrogen carbonate. Now, remembering my balanced chemical equation here was for 3 moles of sodium, because I have 3 sodiums on my sodium citrate over here. For every 1 time I go through this reaction the way it's written, for every 1 mole of reaction, I use 3 moles of sodium hydrogen carbonate. So I'm going to set up the moles of sodium hydrogen carbonate down on the bottom so they cancel, moles of reaction on the top. Now I can go back to my delta H because that is per mole of reaction. So 1 mole of reaction generates 210 kilojoules per mole. And now if you look, you can see how guiding my way with these units, I can see how things cancel. Moles of sodium hydrogen carbonate cancel moles of sodium hydrogen carbonate. Mole of reaction cancels mole of reaction. The unit that's left is kilojoules. That is an amount of energy. So if I go ahead and do this, I take 4.11, divide it by 3, multiply by 210. So I get 288 kilojoules here. So the mole of reaction here is a step that kind of reconciles our stoichiometry with our